Hello. So in this section, the final part of this chapter, we're going to continue our work of inequalities. But this time, we're building on what we looked at last time when we looked at certain inequalities, solving them by looking at the graphs. So, for example, if we had, if we go back to the one example we did last time, if we had these two curves, right? That's g of x, that's f of x. We looked at where, for example, where f of x was less than g of x by considering where f of x was below g of x, okay? So then you see on the left, before it reached the point of intersection, f of x is above g of x, so no. But then we looked at between these 2 points, and actually f of x then is below g of x. So the solution was between these two intersections, okay? So that's sort of a graphical way of solving it, and that's what we're going to look at today. We're going to look at plotting inequalities, drawing graphs, and then actually the solution we can mark by shading the region. So in this case, the region was between these two intersections. So we could shade the solution by actually doing this, right? By marking the area where that inequality is true, okay? And that's the whole premise, right? This allows us this instead of solving an inequality, algebraically like we looked at earlier in the chapter where we looked at solving linear and quadratic inequalities quite algebraically. We instead going to look at in this section solving several inequalities graphically. Okay. Um, so yeah, so some points then what we're going to look at, and we're going to use sort of the ideas that we looked at last time, but we're going to extend it. So first of all, um, we're going to look at another example. So let's have a look at this f of x curve again. Now this time, in this section, we are going to look, instead of two different functions per se, f of x, g of x, we're going to look at what happens when y is less than f of x, or when y is greater than f of x, okay? First, let's do less than or equal to. I'll get more into that in a second. But first, when y is less than or equal to f of x, okay? Well, in the previous section, we looked at two functions where f of x is less than g of x, when f of x was below g of x, okay? We're going to use the same sort of idea here when we have y instead. So we have this function f of x, and we want y. We want the value. We want the inequality y less than or equal to f of x. What that's saying is the y values, or the values have to be the values that we're interested in, the part of the graph we're interested in, has to be below the curve f of x. Okay. So we only have one actual graph, but the y is basically like the values we're interested, the part of the graph we're interested, the whole graph, right? We're interested in. So that's x and y. So the graph we're interested in has to be less than f of x. That's what that's saying. It's top inequality. That means the part of the graph we're interested in is below f of x. Okay. So what that would mean is the region we're interested in is this part here, but it's below or outside the curve, right? So those are the values that would be less than the if we extended it, less than the curve. Okay. Okay, so it's below the curve. Okay. Then what about when y in this case is greater than or equal to f of x? And I'm going to do it in a different color actually. I'm going to do it in a different color. To show that it's different. So instead, if we have y greater than or equal to f of x marked by red, well, that's instead the saying the value, the part of the graph we're interested in is going to be above f of x. It's going to be above the curve. That's going to indicate this part of the graph, right? where it's let me get rid of this, where it's above the above the curve. Okay. Um, so yeah, so that's the idea that we're going to start to use in this section is we can look at the parts of a graph when given a curve, the parts of the graph that are below a given curve, and the parts that are above a given curve. Okay, in a similar idea to what we looked at last time, right? Okay, let me do another example then. Cool. Let's go back to black. Okay, but we're also going to look at lines. So let's have a look at this equation. Let's have a look at this as well. So say we have a given line, right? That's going to be f of x as well. Oh, pretty ugly line. There we are. So that's f of x. In this case, if we want y to be less than or equal to f of x, so this line in this case, we want it to be below the line. Okay, so it's going to be this region here. Okay, that's the region below the line. Okay. And then likewise, I'm going to do an orange to make it a bit clearer. A bit different to red. I think red and black's a bit similar. Anyway, what if instead we want y to be greater than or equal to f of x? So this case, it's saying we want the values of the part of the curve, part of the graph above f of x, so above the line. That's going to be here. Okay. Okay. So the top, the top half of the line. Okay. And so yeah, so those are the regions we're interested in. Okay. Um, cool. So we're going to be using that idea of being above or below the curve. Okay, that's going to help us sketch or solve be able to visualize inequalities visually. Okay. Cool. I'm going to get rid of this because I'm going to go over something else. Okay. Cool. Another thing we need to look at is let me get rid of all this. There we are. Cool. Um, we need to look at the types of inequalities as well. So let me go over a very simple example before we dive into the actual examples, the more complicated ones. So let's say we have the inequality y is greater than or equal to -2. Actually, no. Before we get on with it, uh, um, let's talk about the number, how we can represent inequalities with number lines, which we're used to, right? So if we wanted x is greater than 2, for instance, we looked at this in earlier on in the chapter, how we can visualize it on the number line. If we have 2 here, we can represent this inequality graphically on the number line by a hollow circle. So a circle is not filled in, and then obviously it goes outwards like that. But the whole idea is we do not fill in the circle because we're excluding 2. Okay, it cannot be equal to. If it was equal to, it would look like this. Okay, but it's strictly greater than 2, so it's a strict inequality. So we do not fill in the circle. Okay. However, if we did x greater than or equal to 2, well then instead we would fill in the circle. Okay, because that indicates we want to include 2. Okay, so we fill in the circle. Um, So yeah, so hopefully, so that's the key detail when we did sketch, well not sketch, when we drew the inequality. Depending on the inequality, so if it's a strict inequality like this, or if it or inclusive inequality, so if we include the number, it, it affects whether we fill in the circle or not, right? If we include it, okay. It's a very, very similar premise to what we're going to do now. And again, you would have seen this at GCSE, but this should be a reminder. Okay, but then let's have an inequality that looks like this. Let's say we had y less than or equal to 2. Okay, there we are to keep with the theme. So very roughly, draw a rough set of axes. Well, y is less than or equal to 2. So the premise, what we're going to do with this idea, with this chapter, is we're going to sketch the the inequalities. But how do we do that? Well, it's like an equation. If we had 2x minus 1 greater than or equal to 2, well, you'd basically just treat it as an equality, and then you solve it like normal. And that's what we're going to do here. So instead of solving them like this way, we're going to sketch the inequalities instead. But sketching it, we just treat it as an equal to, right? So instead of y less than or equal to, just going to say y equals to 2. We know how to sketch that, don't we? Should be from GCSE, as a reminder. It's just going to be a horizontal line that passes through y's 2. Obviously, very roughly without a ruler, but it's going to look a bit like that, right? Y equals to 2. Actually, no, I can make that a bit better. Come on. Let's use our ruler. I got it out. So it's basically just going to be a line, a flat horizontal line. That indeed. Oh, this is why I didn't want to use it. There we are. That passes through 2. Okay, there we are. So 2 is going to be about there, right? So it's going to look like that. That's the line, right? Y equals 2. So sketch it like it's an equality, right? Nothing new there. We know how to sketch y equals to 2. However, then, like what we looked at previously, just we want to shade the region we're interested in, so the inequality. Okay, so the space we're interested in. So this is saying y is less than or equal to 2. Again, that's going back to what we looked at. We want the part of the graph, which is y, we want it to be below 2. So we want it to be below the line. So it's going to be this region right here, below the line, okay? So yeah, so we represented that graphically, right? That's represented it graphically. The part of the graph we're interested in that satisfies the inequality. The part of the graph, so y, we want it to be below the line because it's less than. Now, that's less than or equal to. However, the other thing you need to consider is what if instead we had y less than 2? Notice it's a strict inequality. It's different. Well, it's the exact same premise. You would sketch y equals 2. Okay. Oh god, it's rubbish line. There we are. Rubbish axis. There we are. So 2 would be about there. Right, it's the same line. However, in this case, we it looks the same as less than or equal to. There's no difference. We would still shade underneath. It'd be the same region. However, it's a different inequality, so it can't be the same. So what we do is to indicate we don't want to include the 2, like with the number line. Remember, uh, it'd be less than it, or it'd be a strict inequality if it's a hollow, not filled in circle, but it'd be less than or equal to if it was filled in. It's the same idea. We're gonna, instead of filling in the line, we're gonna want to use a dotted line instead. Okay, so we redraw the lines, and when you have a strict inequality, remember instead you want to indicate that by doing a dotted line, which means you have breaks, right, when you draw the line as so. There we are. So instead, your line's going to look like this. So if y equals 2, instead of just being a continuous like filled in line as it is, you want to break up the line like that. So we call that a dotted line. Okay. I'll say that here. So that's going to be a dotted line, which indicates a strict inequality. We use a dotted line if we want to exclude the number, right? So we want to exclude 2 from the inequality, which is what we got here because it's strictly less than 2. If we wanted to include it, then yes, we do what's called a filled line, okay, which means there's no gaps. So we want to include the point 2 as well, which we indicate by filling in the line. Exactly the same sort of idea with number lines like here, right? Um, so notice that this is different to this, okay, because of the fact that the filled in circle is if we have equal to, and then a not filled in circle is if we have a strict inequality, okay. Exact same sort of idea. We fill in the line if we want to include the number, so if it's an equal to as well, or if it's a strict inequality, strictly less than, or strictly greater than, vice versa, we do a dotted line. Okay, so that's what we need to pay attention to, but the region would be exactly the same. Okay, we'd still highlight the part underneath the line because it's less than. Okay, we want the values less than 2. We want it to be less than the line. Okay, so that's a very simple example, but that's what we're going to do. So as a reminder, when sketching inequalities, we sketch it just like by setting it equal to, and then we sketch it like normal. Then we need to consider if we fill in the line, we'll have it dotted by looking at the inequality, okay? And then we fill in the region by looking if we want it to be above or below the line or the curve, okay? And yeah, okay. So that's a simple example, but actually, the where this gets useful is when we have multiple inequalities, okay? Because then it can be a quite arduous, it could even be difficult, or even not even be solvable if we have particular inequalities. So, for example, it might be difficult to solve an equation, but we know what the graph is, okay? Um, so, for example, if we had y is equal to x and y is equal to cos x, if we wanted to solve x equals cos x, that we can't really do. We don't really have techniques to solve it exactly. At least, what you study in this course anyway. Uh, but we know the graphs x and cos x very well. Okay, so if we could sketch these two graphs, then we could solve an inequality. So if say was x was less than cos x, we could solve that quite easily visually on the graph. We know visually where the region is, the values that we want. But solving it x equal to cos x could be quite well. You won't be able to solve it, even though we know the graphs are quite nice. So anyway, there is advantages to doing this graphically, and that's what we're going to look at. Okay, uh, okay, let's waffle in and let's actually move on to an example. Okay. Okay, so this example says on graph paper, shade the region that satisfies the inequalities. Okay, so it's firstly y is greater than or equal to -2. So we're going to want y equal to -2. We're going to sketch that first, okay? So on graph paper, so we need to try and draw it kind of exactly. Well, I've got square paper here, so we can use the squares as a scale. So -2, y is equal to -2. That's going to go through there, right? If we label this x and y, the axis, there we are. So -2 is just going to be there. But hang on, before we draw the line, does it have to be a dotted line or a completely solid line? Let's have a look. It's in equal to inequality. So it needs to be a filled in line, okay? So we can just simply draw the line. There we are. So that'd be y equal to -2. Okay, now the last bit, okay, we're not going to worry about the inequality just yet. We're not going to worry if it's above or below the line yet. But I'm going to plot all the other inequalities first, okay? And then we can sort of do that afterwards. Let's just focus on getting all the inequalities on before we actually start solving or finding the region we're interested in. Anyway, let's do the next line. About x less than 5. But that is also a line because we want to set x equal to 5, okay? So we can draw that as well. Because this time it'd be a vertical line. Remember from GCSE? You should be familiar with drawing equations like x equal to 5 or y equal to -4 as horizontal or vertical lines. Okay. So x equal to 5. So find 5 on the x-axis. It's going to be 1, 2, 3. It's going to be there, right? So our line's going to go through there. However, before we draw the line again, is it going to be dotted or filled? Well, look at the inequality. It's a strict inequality. It's not equal to. So it's going to be a dotted line because we want to exclude 5. So there we are. So make sure we do dotted. Cool. There we are. And then that's going to be x equal to 5. Okay. Then we have y less than or equal to 3x plus 2. So that's first of all just the line y equal to 3x plus 2. If you set it equal to, remember it's like solving an equation. You set an inequality. You basically solve it like an equation. That's what we're going to do. Treat these different lines as equations because we can sketch them. Okay. Then we deal with the inequality bit after. Anyway, so we're going to plot the line y is equal to 3x plus 2. So that's more complicated than the other two. But how do we plot lines? Well, with the multiple ways, you can try and work out the gradient and the y-intercept. But I tend to like doing it by just finding any 2 points on the line. By doing that, I could just substitute any 2 points, any two values of x and y. So let's keep it simple. Let's pick x equal to 0, firstly. So when x equal to 0, remember for y it's 3x plus 2, y would be 2, okay? And then that would give the coordinate 0, 2. So I can plot that on my graph. So it's going to be there, right? Then let's pick x equals 1, the next point up. So I'm picking simple values for x, right, to find any two particular coordinates. Then when x equals 1, y would be 5. Okay, 3 lots of 1 add 2 would be 5. So that would give me 1, 5, which should be, oh no, 0, 2, sorry. 0, 2 would be there, sorry, on the y-axis. 1, 5 would then be there, right? Cool. Okay, cool. So then I'm going to draw the line. So let's match my ruler up. So how am I going to draw the line? I'm just going to connect the 2 points. Draw a line between the 2 points. So, about there. I think that should be okay. Now, last thing before we draw it, I have to look at the inequality, and it is less than or equal to. So it's an equal. So it's just a field line because it's an equal to type of inequality. It's less than or equal to. So we could draw the line. There we are. Is it matched up? I think I need to tilt it a bit more. There we are. Maybe it's just being a bit paranoid, but there we are. That's the line we have. Cool. So that'll be the line y is equal to 3x plus 2. Cool. Then finally, we have this last part here. What x greater than 0? But that's also just x equal to 0. If we just take out the inequality, put equality and equal in, and then we sketch x equal to 0. Well, actually, funnily enough, x equal to 0, well, that's just the y-axis, isn't it? Because x0 is, uh, oh, here, it's just the y-axis, isn't it? Because that's when x is 0. So it's a bit awkward drawing it when that's the y-axis. Okay, but look, we have to draw over the y-axis then the best we can. But then if we draw the line, again, look at the inequality, it's strict. So we have to draw a dotted line. So, weirdly enough, we kind of have to draw over the y-axis and then draw dots. But we're not going to we're not going to be able to do it very well. I don't know. I have to just leave it there. Hopefully you can kind of see the dotted on the y-axis, but that's very unfortunate. That's a very unfortunate line to draw. Anyway, so we marked our lines. Okay. Now the last thing we need to do is to work out the region. So we're going to look at each line in turn, or each inequality in turn. So the first one was y greater than or equal to minus 2. So let's look at our line y equal to minus 2, which is there. Okay. We want y to be greater than or equal to. So we want the part of the graph, the y, to be above minus 2. So we want it to be above the curve, right? So if we indicate our region, let's do it in yellow again. So firstly, it's going to be above the line y is equal to 2, right? There we are. Okay, and then the next inequality, x less than 5. I'm going to mark that with a different colour. Let's do green. There we are. X less than 5. So x is equal to 5 is here. Okay, if we want it to be less than 5, we want it to be on the left side, okay, of the line. Because we want the x values less than 5. Okay. Um, so we want it to be on the left side. So we already want the parts that are in yellow, right, that I've marked. That's the region we're interested in. But we also want the region that's on the left of this line here because it's less than 5. Uh, I'm gonna overmark it in green if that's clear. So there we are. So that's the new region we're interested in. Okay. Okay. Then let's do another color. Let's do pink. Okay. Then we want y to be less than or equal to 3x plus 2 when we draw the line here. So we want the y, the part of the curve, to be less than or equal to less than. So we want it to be below the line, below the part of the graph below the line. So if the line is there, well, it's going to be, well, combining the regions we already shaded, it's going to be this part, isn't it? Okay. Cool. So the three bits are shaded, which is in pink as well. That's what we got up to. Now we've got one final inequality, which is shall we do that in um indigo? Okay. The final part is x greater than 0. So remember x was just we should mark that here. X equals 0 is there. That's the y-axis because that's also x is 0. We want in this case we want x to be above 0. So we want the values of x bigger than 0. It's going to be on the right side of the y-axis. Okay. So it's going to actually then be these values here at this part of the region. So we want the region on the right of the y-axis. Okay. So the final region we get, to really make that clear, it's a bit awkward drawing multiple inequalities. Um, Apologies if it isn't pretty clear. Uh, but um, what pen should I use this one? Here we are. So the final if we then the final region where all four colours, so all inequalities are shaded, is actually going to be this. Oh, oh, this region here, right? I've probably done that terribly. There we are. That's sort of weirdly like trapezium type shape. There. Okay. That's the final region of interest. That's the part of the graph there. Okay. And then there we are. Cool. Okay. So that's it then. So that represents. So if that's saying if you pick any x value or indeed any y value as well. So the combination x, the coordinates, right? So remember we have y and x and y here. Any coordinates x and y you pick in this region will satisfy all four of these inequalities. You plug those values in. Okay, and we can actually use that idea to help us test whether our region is correct. If you are at a point where you're unsure if a particular region is indeed true, you can test your answer by picking a point in the region you suspect is true. So if I suspected this region are marked in red, so the perimeter, the edges in red, anything in the region I suspect is the region, right? I could pick any point in the region. Let's say, oh, it's a bit awkward because it's all sketched in, but hopefully you see that the point 1 1. Oh, oh, that's a bit thick. There we are. Hopefully you see that the point 1 1, which would be here, that would be in the region. Okay. Then what we can do is we can test this point 1 1 by substituting it into every inequality. If your coordinate you pick, we call it a test coordinate. If you pick a test coordinate to test your answer, right, to see if the region is actually the region, you should it should your coordinate should satisfy every inequality. So let's do that then. So firstly we have y greater than or equal to minus 2. So y would be 1. So we'd have 1 greater than or equal to minus 2. Yep, that's right. Then we have the next inequality, x less than 5 or x equal 1. 1 less than 5, that is true. Then we have y, which is 1, is less than or equal to 3x plus 2x is 1. So 3 lots of 1 is 3, add 2 is 5. 1 is indeed less than or equal to 5, yep. Then lastly, we have x is greater than 0. So 1 is greater than 0, yeah, that's true. So because all inequalities are true, then actually your region should be correct then, okay? And there we are, so that's our final answer. Uh, it's a little bit messy. I actually probably wouldn't advise drawing so many lines, and so many dashes, but yeah, that should be right. Okay, cool. So have a look at an example then. We have less inequalities now, so this should be good. It shouldn't be as distracting or unclear. Anyway, we have this example. We want to shade the region satisfying the inequalities 2y plus x is less than 14. And y is greater than or equal to x squared minus 3x minus 4. So recognize that this is a quadratic. So you don't have to, it won't just be lines. It could be any graph, really. But we can apply what we've done to any particular graph. So firstly, we need to draw this line. 2y at x is less than 14. Exact same parameters. We're going to set it as an equation, which we can sketch, okay? So how are we going to sketch it? So this is going to be the x or y axis. You're just going to pick, well, anyway, but I do recommend it. Just pick any 2 points on the line by substituting any two values of x or y to then find two coordinates to connect them. So any two values, we could have x is 0, but then y would be, well, 2y would be 14 then y would be 7. So that would give the point 0, 7. Then I could pick x equal to 1 next. I would understand that. But we would have 2y plus 1 equal 14, so 2y would be 13. That will give me a fraction. I'm not particularly keen, so if I just pick the next number up. So then when x is 2, then 2y would be 12 instead. That would give y equals 6. So nice whole numbers, okay? 2, 6. I can mark these 2 points on our curve. So that would be 1, 2, 3, 4, 5, 7, 0. So that would be 0, 7. Then 2, 6 would be here. There we are. Okay, then we just draw the line. So the line that connects the 2 points. Okay, so let's get our ruler. Du, du, du. Mm, uh, oh, there we are. That should be good enough, I think. Okay, I'll leave it there. Okay, so we draw the line then. So that'd be the line. However, again, I need to pay attention to the inequality. It's a strict inequality. That means we need to be dotted to exclude. Okay, so we draw the line, but it's going to be dotted. Okay. Oh, there we are. Cool. So then that'll be the line 2y add x equals 14. There we are. Then we need to plot this, what's it called? This quadratic, no, yes, quadratic. I'm going to do that down here. Y is equal to x squared minus 3x minus 4. So I need to sketch this quadratic. We'll probably draw it ideally. So again, we looked at sketching or drawing quadratics in the last section, which was called quadratics. So we can use the key details to help us. So first of all, the y-intercept would be minus 4. So when it crosses the y-axis, it'd be minus 4 down here, because that's when x is equal to 0. Okay. We could then find the roots. Are they nice roots? Uh, Um, Remember, the calculator will have a quadratic solver, so you just use that very quickly to get the roots. Okay, and actually the roots are x equals 4 by just putting in the calculator, or minus 1. So we can also plot that on our graph. So x equals 4. That's going to be here. and x equals -1 be there. So that'd be the root of the quadratic. Okay, we could find the turning point. But I'm not sure. Nah, let's do it. Let's just test what we've done. So then we can find the turning point to help us even more visualize what the sketch would look like. So the turning point, remember, comes from completing the square. So we do x and then half of -3 with -3/2, all squared. Then I'm going to do minus the square of that, -9/4, -4, because we have a -4 at the end. Then we could just simplify it. So we have x -3/2 all squared. And then we put that bit in the calculator, -9/4 at -4 will get me minus 6.75, 6.25, sorry. Okay. So that means the turning point is going to be at, well, set the bracket equal to 0, so that means x is 3/2, which is 1.5, and then the y value is -6.25. So roughly, if that's -4, the y-intercept there, then -6.25 is going to be about there. So 1.5. So the turning point is going to be about there. Okay. So the turning point is 1.5 -6.25. Okay, so that were. I think I've got a good enough idea about what the quadratic will look like. So it has to pass through the roots and the ones. Well, it has to pass through all 4 points actually. So I reckon, and please make it be somewhat presentable. I'm not the best at sketching. It's gonna be a quadratic that oh god, looks like that. I could do a bit better than that, I think. Actually pass through the y-intercept. Okay. Uh, let's do it again. There we go. Nicely. Okay, I'll accept that. There we are. So that's what the quadratic would look like. So that'll be y equals x squared minus 3x minus 4. Also, make sure you do label it to just make it clear what graph you're sketching, and it isn't equal to, because if it was because that's what we sketched. Okay, we're sketching the actual equation bit. Okay, so we drew two. I forgot to check. Before we sketched it, we should have checked the inequality. Even though it's not a line, but we still have to check the inequality. And actually, it isn't equal to, so it will be a filled-in inequality. If instead it was y greater than, strictly greater than, it would have to be a quadratic that is dotted. So instead, it would look like that, okay? But if we can just fill it in because it's equal to. There we are. Okay, so there we are. We're all fine. Okay, then we got two graphs. Now we need to find the region, so we need to actually consider the inequality. So first of all, we want 2y and x. Well, it's less than 14. So we want the line want it to be below. Okay. So we want to be below the line. So oh, hang on, one thing. So it's going to be the region I'm going to shade uh, here, right? So it's going to be below the line. So it's simply going to look like that, okay? Then we need to consider the other inequality, y greater than or equal to x squared minus 3x minus 4. But instead, that's the y, the part of the graph is going to be above the quadratic, okay? So above the quadratic, so the part of the graph above the quadratic curve, that's going to be uh, this region here, where it's both the region above the quadratic but also below the line, which is in orange. So in pink is both the region of the quadratic that's above the quadratic and below the line. So in our pink shaded region, our pink shading is the final answer. That is the region, okay? And again, we can test the coordinate to see that it actually is the pink region I've shaded. So pick any coordinate in the pink region. We can spot, well, simply 0, 0, right? The origin is in the line. Keep it simple, right? That's a point in the region. If I think pink's a region, let's do a test coordinate. So test 0, 0. And what that means is I'm going to substitute x and y0 into these two inequalities, and it should be true. So firstly, 2 y at x less than 14, while y and x 0, so that'd be 0 less than 14. Indeed, that's true. Then we have y, which is 0, greater than or equal to x squared minus 3x, that'd be 0 minus 4. Where indeed 0 is greater than or equal to minus 4. So that means the pink region should be the shaded region. Okay, there we are. So again, to really illustrate the region of shaded, that is going to be uh, here, but also then the line. Okay, so everything inside the red sort of perimeter, the region inside the red, which is in pink, right? Inside the red perimeter, in this case, the red is like the boundary, right? The outside of the region. Inside the red would be the region we're interested in that case, okay? Just to really hopefully I could visualize, show you how to visualize the answer. Um, Now, of course, in the exam, you won't be able to write in different colours. However, the examiners will be, they will obviously be lenient. They know it's going to be a little bit awkward sketching inequalities like this. I haven't really actually seen many exam questions in the A level that ask you to do this, but they will be a bit lenient um, and what you can also do as well is mark your region. We can call the region R as well. Um, which stands for region, right? So the region we're interested in, we can mark it as R if you're worried about the colours or the whatever or the shading, making maybe it's not unclear. But anyway, there we are. Okay, let's have a look at more examples. And actually, what they could also ask you is to do the reverse, right? Instead of you finding the inequality, the region. So remember, the region consists of all the points and coordinates that satisfy all the inequalities. But so, like we did here, substitute any coordinate in, and it will satisfy all the inequalities. That's what we've done there. Is solving the inequalities on a graph, okay, visually. So showing visually where the points are. We can go backwards, and given the region, that might actually define the inequalities that define the region. Okay, so we're going backwards. This is more of a common exam question, so they normally ask you this sort of thing instead. Anyway, so let's have a look at this example. So they're given this sketch which shows the graph of the straight lines with equations y is equal to x plus 1, y is equal to 7 minus x, and x is equal to 1. And obviously the sketch has shown all of them there. Okay, cool. Hang on. Why is my pen thick? Uh, there we are. Cool. Okay, part A is saying to work out the coordinates of the points of intersection of the functions. Okay. So the intersection with all the lines. So obviously this is going to be an obvious one, but also x is equal to 1 as well. So it's going to be these 2 points as well. So there should be 3 intersections. How we're going to work that out is to equate any 2 lines together. So firstly, let's do y is equal to x plus 1 and y is equal to 7 minus x. We can call that 1 and 2. Um, and these are simultaneous equations, right? Remember that the intersection of 2 lines or 2 graphs or 2 curves means they can be solved simultaneously. Okay, so that's what we're going to do. So we can substitute one to the other to solve it. Let's sub the first one in, the first equation, because that's y, and I'm going to sub that into the second equation. So y, the two y values are equal, so that means x plus 1 is equal to 7 minus x. Then I'm going to move, I'm then going to have 2x, and then I'm going to have equal to 6, right? If I move the 1 to the other side, take away 1, then x is equal to 3. Okay, then I need the y value. So then if x is 3, well then substitute that into any of the equations. So y is x plus 1, then that means y is equal to x plus 1. That'd be 3 plus 1 equals 4. So the coordinate there would be 3, 4. Okay. Okay, then we need to find another intersection. So then let's do y is equal to x plus 1 and the other line, which is x equal to 1. Okay. Now this one's quite easy to solve because they already give you the x value. X is equal to 1. So if x is equal to 1, then y is 1 plus 1, 2. So they're simply the coordinates 1, 2. So no substitution needed because it already give you the answer pretty much. Then the final intersection. Well, we already considered the first line, the other lines. Then we need to consider this line and x equal to 1. And x equal to 1. Okay, well then, again, quite easy. X equal to 1, and y is 7 minus 1, which is 6. So that'd be the 0.16. There we are. So those are the 3 points, okay? Cool. And hopefully, again, you can use the graph to make sense. So 1, 6 is here. Great, that is clearly 1, 6. 1, 2 is there, so that's right. And then this other intersection point is 3, 4, is it? That's what we've got, 3, 4. So, yeah, we've done it right. Okay, that's part A. Then part B says, write down the set of inequalities that represent the region that's shaded. Well, we're working backwards. So in this case, we need to consider the inequalities. So what we need to consider is all these lines given to us, and we need to consider whether the region is above or below the lines. And also the type of line as well. Is it a dotted or is it a solid line? Those are the two things we need to consider, right? Um, yeah, so let's consider line by line. So firstly, y is x plus 1, this line here. Well, clearly it's above the line, right? The region is above. So that's going to be y is greater than x plus 1, okay? So it's going to be above the line x plus 1. Now, is it greater than or greater than equal to? So establish it's greater than, but what type of inequality is it? Well, it's a solid line, it's filled in, so it's going to be equal to. And there we are. So that's the first inequality. Okay, that's the first one. What about this line then? Y is equal to 7 minus x, the red line. Well, if you notice, the region is below that line, right? It's below. So that means y instead has to be less than 7 minus x because the region is below the line, so it's less than 7 minus x. Okay. Um. Okay. Again, then is it less than or less than or equal to? Right. It's a filled in line. Okay. So it's going to be equal to. So it's less than or equal to 7 minus x. Cool. Then lastly, we have this inequality. We have the last line x equal to 1, right? Uh. Well, again, is it to the right or to the left? What side of the line is it on? It's on to the right, isn't it? It's to the right of the line. So it's going to be bigger than 1, isn't it? And then lastly, is it greater than or is it greater than or equal to? What type? Is it a dotted or filled line? Well, it's a filled line, isn't it? The blue line again, it's filled. So it's going to be equal to. And those are the 3 inequalities that make up the region. Okay, so you can see there we work backwards. Okay, to work out the inequalities. Okay, now we've got some exam questions. Okay, so this time we are given a figure 3 which shows a sketch of the curve C and a straight line L. Given that the C has the equation y is f of x, where f of x is a quadratic. Wow, so it's telling us it's a quadratic curve. Okay. C cuts the x-axis at 0 and 6, so X crosses the x-axis here and here, and L, the line L, cuts the y-axis at 60, that's there, and intersects the curve C at 1080. They're giving all the information on the curve, right? It says use inequalities to define the region R. So it's exactly kind of like the last example, right? Where we need to find the inequalities to get to that define the region rather than finding the region using a given inequality. We need to work backwards again. So that's what we're going to do. So again, we're going to consider all the types of lines and curves we have. So firstly, we have the line, okay? Well, again, think about it. Is the region below or above the line? It's below the line, isn't it? Right? It's below the line. So that means for our line L, we want Y to be less than L. Okay. Um, okay, and then it's less than, but is it less than or less than equal to? It's gonna be less than or equal to because the line is not dotted. Okay, it's filled. Okay, so it's not dotted, it's filled. So it'd be less than or equal to L. Now L is going to now L is a line, so it's going to be Y. It's going to be Y equals mx plus c. Okay, that's the general equation of a line. We're going to have to find that line. Okay, it's not good just saying Y less than or equal to L. We need to find exactly what that line equation is. We'll get to that in a minute. Let's just find the inequalities first. Okay, so that's the line. Now we've got this quadratic. Okay, so again with the region, with the quadratic, is the region above or below the quadratic? It's above. Okay, so it's above the quadratic. So that means y is going to be bigger than the curve c. The c is the quadratic. Okay. Again, so that's greater than, but is it going to be greater than or equal to? It's going to be equal to because the quadratic is a solid line. It's not dotted. Okay. It's a filled. It's just a nice filled in line. So those are two inequalities. Okay. But that's not good enough. Obviously, we can't just say that, especially for 5 marks. What we then need to do is this is the other part of the question. We need to work out what the curve and the line is, the equation. Well, we already said we know the line is y equals mx plus c. Let's find the line first. Y equals mx plus c. We need to find the gradient and the y-intercept. Okay. Um. Well, actually, what we can do is we know 2 points on the line. We know this point and this point lies on the line. We can use that to find the equation. So firstly, we have the point 0. Well, what's this coordinate? 60. The y coordinate is 60. So and it's on the y-axis. So x is 0, y 60. Okay. So we can then substitute that into our equation. Okay. So when x is 0, y is 60, we're going to get 60 is equal to mx. Right, m not for 0 is 0. So 60 is just equal to c. So we could say y is mx plus 60, okay? And that's the y-intercept, right? We could even just write that down, right? We could simply say, you should know that c is the y-intercept, which is 60. But anyway, there we are. We have mx plus 60, then we know the other point on the line is 1080, okay? So I'm going to substitute that point in as well. So y is 80, and x is 10, so it's going to be 10m add 60. Then we need to find m. So 10m is going to be 20. Move the 60 to the other side. That means m is going to be 20 over 10, which is 2. Therefore, our line is 2x plus 60. Cool. So that's our line. So that means y has to be bigger than the line. Okay. So therefore, y has to be bigger than the line. Okay. Remember, we discussed that just right. Y be less than or equal to L, sorry. Has to be below the line. But we know what the line is now, we work that out. So there we are. So that's the line. Then we need to find the quadratic, okay? We did look at, this is a bit complicated, but we did look at examples when we looked at modelling the quadratics. We looked at various exam questions where we needed to find a quadratic expression. It's the same sort of idea again. So we need to work out the quadratic. Okay, because we can't just say y greater than or equal to c. That's generic. That's not specific. Okay, we need to find exactly what the curve is. So we know it's a quadratic, so we need to work that out. So what are we given with regards to the quadratic? Well, we know what points lie on the quadratic. This point, but also these 2 points, and these 2 points are the roots. So that can help us. So we know the two roots are x equals 6 and x is 0 on their roots, right? Then we can, so those must be the factors, okay? So remember, we then would factorize to get the solution. So x minus 6, well, x minus 0, but that's just x, okay? And then if you set that equals 0, then you get the solution, okay? So those are the factors. Well, then just to get the quadratic, we would expand it then, right? Because then we're working backwards in a way. So we factorize it. To get the quadratic expression, we can expand the factors. However, um, I did went over this when we looked at quadratic modeling as well with a very similar type of question. When you're going the other direction, when you're going from the solution to finding the quadratic, usually go from the quadratic to the solution, right? Because that's what you want to do. You want to solve it. But in this case, we want to go backwards to find the quadratic. What you need to pay attention to is that actually there would also be a coefficient a. Now that would come from ax squared, right? If we were to expand this, we would just get x squared. But we need to account for the fact that could be a number in front of the a, in front of the x squared, which would be a. And why is that? Well, actually, think about it. If all of this is equal to 0, then each factor would be equal to 0. But a is also a factor in a way, right? Isn't it? Because a is also a number being multiplied here. But a would not be 0. Okay, so we could then just divide by a to then only get these two numbers. Okay, to then solve it. However, we need to account for the fact when we're going backwards, there would be a number in front of it. Okay, which would be the coefficient. Okay, and it'd be a number a. Okay, and the coefficient of a, because if we could just then cancel or divide. We can divide by the number because it's equal to 0. Because remember, say if we had 2x equal to 0, right? We can then cancel it down to x because we're just dividing both sides by 2, okay? And it's the exact same thing, okay? It's the exact same idea, but when we're going the other way around, we need to account for the fact there might be a coefficient in front, okay? When we're dividing through it. So we need to account for a number in front of it. So there we are. So what we're going to do is I'm expand it with a number in front. Let's go for it then. Okay, so we're going to have a, and then we're going to expand the bracket. That's just x squared minus 6x, right? Times x by x minus 6. That would be ax squared minus 6ax. Okay, so that is the quadratic, but then we obviously need to find a. Well, we know what another point is. It's 1080, right? That also is on the curve. We can substitute that point in to find the value a, because y is equal to ax squared minus 6ax. Y is the quadratic. So if I substitute x is 10 and y is 80, 80 would be ax squared. That would be a lots of 10 squared, and that's an a, not a 9. Minus 6a lots of 10. If I then expand it, the brackets will get 80 is 100a minus 60a. Then I would get 40a equals 80. Then I get a is 80 over 40, which would be 2. Cool. There we are. And so therefore our final quadratic is 2x squared minus 6a. 6 times 2 is 12x. There we are. Okay. Now, if you were, especially for the first time, it is very, very difficult to just be able to realise and remember. You need to account for a number in front. Okay, but you could check if something's gone wrong. If he left out the a and just had x squared minus 6x, if you then substitute this point in 1080, you would go wrong. Okay, you wouldn't get that wouldn't satisfy the equation. If he substituted 1080 into here, you would get 80 is 100 minus 60, and that's equal 40. But clearly 80 is not equal to 40, okay? So you'd know you'd have to account for something because something's gone wrong there. So that's why, again, it's, check your answer, right? Anyway, with that said, we've got our quadratic now. Well, again, we discussed that the region is above the quadratic, right? So the graph has to be above, the y has to be above the quadratic. Remember, discussed that over here. So Simply then, y is going to be greater than or equal to 2x squared minus 12x. Therefore, if we combine it, our final answer is, if we combine these two inequalities here, we get y is less than or equal to 2x plus 60, and y, and not or, but and, because both of these have to be true, okay? Okay, for that region. Anyway, so we have and y is greater than or equal to 2x squared minus 12x, okay? There we are. So that is our final answer. Now you could think, well, what if we could solve that inequality? Perhaps we wanted to simplify it, but we don't have to. Okay, it just said give an inequality. This is an inequality. Okay, we don't need to be any more. We don't need to be more specific. We don't need to solve or break it down anymore. As long as you give a inequality that represents, that's fine. But we did need to find the curve because we can't have any missing values. Okay. So yeah, there we are. So hopefully you see it's the same sort of idea. Okay, even though it's a bit more complicated, we have to find the functions, but it's not too bad, right? As long as the idea of, again, whether you have to go below or above the curve or the line or so forth to get the region. Okay, we're going to finish off with one more exam question. It's very similar, okay, again. And hopefully you recognise, again, you start to pick up the idea, and also you start to understand the exam questions more. Okay, so we have figure 1, which shows a sketch of a curve C with equation y is f of x and a straight line L. The curve C meets the line L at points -2, 13, which is here, and 0, 25, which is there. Okay. The shaded region R is bounded by C and the line L. Given that f of x is a quadratic again, and -2, 13 is a minimum turning point on y is f of x. Turning points on a quadratic, think about what that means. Use inequalities to define R. Again, the same idea, we need to find inequalities. Again, the region is marked by the line L, right? And it's also marked or defined by the quadratic. So again, a very, very similar example. We need to determine the inequality, whether it's below or above the line and the curve. So let's deal with the line first. So the line is L again. So Y and L. So firstly, the line L, which is here, right? Is the region above or below the line? Oh God, I can't draw the line. Is it above or below the line? Well, it's below, isn't it? Right, if the line and it's below, it's underneath, right? So that means Y has to be less than L. Again, again, then. So what type of inequality? So we know it's less than. Is it less than or equal to? Yes, it is, because it's a straight line. It's a straight line. It's a filled in line. There's no dots. Okay, it's not dotted or broken up. Okay. Okay, so that's one part. Then the quadratic part. So the quadratic, okay, we have the region there. Is the region above or below the quadratic? It's above again, isn't it? Okay, it's there. Okay, the region is above the curve, the quadratic. So that means y has to be bigger than c, which is our quadratic, our curve, our c. It's our quadratic. Again, then, is it greater than or greater than equal to? Well, it's going to be equal to, because again, the quadratic is again a nice filled in line. Okay, cool. So again, the mission really there, again, is to just find what L and C are. Okay, so are we going to do that? Well, so we've got the main question, right? We've got our inequalities. Now we just need to find the line and C. Firstly, L, the line. The line is going to be y is mx plus c again, isn't it? So we also need to find m and c. Firstly, we know the y-intercept is 25, so that means c is 25. So y is mx plus 25. Okay, now we need to find m, the gradient. Well, we can find that by substituting a point in. We know a point is -2, 13. -2 minus 13, right? And -2, 13, sorry, positive 13. There we are. So substitute that point into our line equation. So y is 13, mx, so m is 2, the x is 2, so it'd be -2m plus 25. Okay, then that means minus 2n is going to equal 13 take away 25, that'd be minus 12. Uh, if we move the 25 to the other side, then we get then m, if we divide by minus 2, that's going to be minus 12 over minus 2, that'd be positive 6. Okay, therefore our line is y is 6x plus 25. And again, then to reiterate, that means that inequality, we discussed this, but the region is below the line. Okay, so that we want the part below the line, underneath the line. So y is less than or equal to 6x plus 25. Okay, so that's one inequality. Then we need to deal with the quadratic. And again, we need to find the quadratic in order to get the inequality. So, we need to consider all the points and information we know about the quadratic. So we know this point lies on the quadratic, as does this. Okay, but this time we only got 2 points. That isn't really enough to work it out by its own. However, this point again, I did talk about this. I made a comment about it just a second ago. That this is a minimum turning point. Okay, I did say think about how that relates to a quadratic. How do we deal with that? Well, you should know with turning points of a quadratic, we complete the square. So actually, it's ideal to consider the completed square form of the quadratic. So it's going to be x. So minus 213, right, is the turning point. So our completed square form is going to be well, the x coordinate of the turning point is minus 2. So we're going to want minus 2, add 2 to make the bracket equal to 0, right, for it to be a turning point. So that means then we're going to have x plus 2 squared. Actually, no, I'll tell you what, I'm going to break it down a bit more. The completed square form looks like this: x plus b, right, all squared plus c, okay? Uh, And then remember, we have a coefficient in front, okay? Again, this coefficient accounts for the fact that we have it could be ax squared, okay? So we have to adjust for a coefficient in front of the bracket. Okay, so that's our complete square form. So that's going to help when we have a turning point, okay, to find the quadratic. So the turning point is minus 213. That means that firstly, for a turning point, remember, or a minimum point, the bracket has to be 0. So that means x plus b has to equal 0. But we know the x coordinate's minus 2. So minus 2 plus b is equal to 0. Therefore, b is equal to 2 if we solve that. Likewise, when the bracket's equal to 0, then that means the y value must be c. Okay, but we know the y value is 13. That means c is equal to 13. Because this is y, by the way. The y equals the whole expression. So when that whole bracket is equal to 0, I'm just left with plus c, okay? So that means the y coordinate of 13 has to be c. So that means y, we could fill these information in, these values of b and c. So y is a, lots of x, plus 2, all squared, plus 13, okay? Okay, and then remember, we can get back to the quadratic by expanding the bracket. But before we do that, we need to find a. How do we find a? Well, we need another point, and it's this point. This point also lies on the quadratic. That point is 0, 25, isn't it? Right, the x coordinate is 0 and y is 25. So again, we're going to substitute that point in. So when x is 0, y is 25. So 25 is equal to a lots of 0 add 2 all squared plus 13. 25 then is equal to a lots of 2 squared, that'd be 4a plus 13. Then that means 4a is simply 25 take away 13, that'd be 12. Then a is 12 over 4, which should be 3. Therefore, our quadratic equation, our complete square form is y is 3 lots of x plus 2 all squared plus 13. Then we just need to get a quadratic, right? A quadratic expression. Remember, it has to look like this: ax squared plus bx plus c. So we need to get it in this form. So we could just expand it, right? Expand the bracket, so we get a 3 lots of x plus 2, x plus 2. Remember, if you have a square, it moves the times by itself. Expand that, we're going to get 3 lots of x squared plus 2x plus 2x is plus 4x plus 2 times 2 is 4 plus 3, 13 at the end. Then we expand that times by 3, we get 3x squared plus 12x plus 12 plus 13. We then get 3x squared plus 12x plus 25. Okay, and that'll be y. Okay, y is equal to all of that. Okay, so that's our final quadratic expression, right? It's in this form. Cool. Now, we already discussed then that the region has to be above the quadratic, right? So the quadratic's there, it has to be, the region is above it. So we want y to be bigger than, or greater than or equal to the quadratic. So that means y is greater than or equal to 3x squared plus 12x plus 25. Okay, there we go. We've got our two inequalities. Okay, there we are. So therefore, our final answer. So our answer is the region is, well, the inequalities are y is less than or equal to 6x plus 25, and the other inequality, y is greater than or equal to 3x squared plus 12x plus 25. There we go. Oh man, there we are. Okay. So hopefully you recognise what we've done there, right? The main premise, right, was just establishing the inequalities, right? Obviously, then we had to do a bit of work to find what the line and the quadratic equation is. But again, we know how to do that, right? This is just piecing basically the whole course together. We looked at in the previous section how we find a quadratic equation given a graph, right? We looked at that when we looked at modelling, where we got given a quadratic graph and we needed to find the um, the quadratic curve, right? It's the exact same idea here, but this time we're stretching it by also considering inequalities, right? So we're linking to what we've just learned, okay? And hopefully you did spot that wasn't too bad, right? We then determined again the region is marked between the line and the curve. So then we considered is the region above or below the line and the curve, and that's what we've done. We learned how to do that, right? So yeah, that's really it, right? So it looks like a lot, right? But nothing ever done, right? Up to this point. But yeah, so hopefully you can see what we've done there about the inequalities. All we did was consider whether we want the region or the part of the graph to be above or below the given line or the given curve. Okay, that's all we've done there. And then we did some more stuff there. But yeah, uh, there we are. So hopefully that's sort of familiar. So remember, we can firstly sketch the region by drawing the individual lines or the individual curves, and then you merge all the regions together, right? By considering if you want to be above or below the line or the curve, right? Because remember, if we have, again, to reiterate, if we have a line above the line when y is bigger than f of x, it's here above the line. And then if you want it to be less than f of x, you want to be below the line, which should be there. Likewise with a curve, okay? A curve here above the curve would be here. If we were to continue it on, it would be in between. Then outside would be less than. If you want to be less than f of x, less than the curve, we want the part of the graph a bit underneath the curve, so it'd be here. Okay, there we are. So there we are. So that's the end of this chapter. That's inequalities. Hopefully, you can see how we can deal with inequalities using graphs. Okay. Um. So yeah, I'm going to leave that there then. So I'll see you next time.